Welcome back everyone. In this lecture actually we will see some basics of representation theory. So, I will define all the terminologies that are used in the representation theory in this lecture, and then later we will develop SL2 representation theory, which will play a very crucial role in the structure theory of semi-simple Lie algebras. So, here are some definitions. So, we will actually work again over complex numbers. So, all representations are again assumed to be over complex numbers. Okay. So, what is a representation? So, basically a representation is a Lie algebra homomorphism from G to GLV for some V. Okay. So, a representation a representation of G is a Lie algebra homomorphism from G to GL of V. Okay. So, here G is given Lie algebra and we are talking about representation of that, and V is vector space over complex numbers. Again in this lecture we will only actually talk about only 5 dimensional representations. Okay. So, basically you can say that a representation is a tuple, okay, V comma phi, if you want to emphasize both V and the action of G on V. Okay. So, this also you can call it a representation. So, here some of the important things I want to actually emphasize. Okay. What is representation? Okay. If you think about it, so a representation of any algebraic object. Okay. So, basically you want to act algebraic object on some vector space, so that each element of that algebraic object can be represented as some linear operator or matrix with respect to some basis of that vector space. Okay. So, in particularly given x, so this given x in G, this x acts on this capital V. So, via this phi. So, what is the meaning of that? So, phi of x is just a map from V to V, that is all it means. So, which is a linear map. Okay. And if you think about this association, x goes to phi of x. So, this is actually a giving a map from G to GLV. So, this association must preserve the algebraic structure that we are actually dealing with. So, the algebraic structure on the left side is actually Lie algebra structure. Okay. So, Lie algebra structure is a vector space with some additional properties. So, that means this x goes to phi x must be first of all linear map and as well as preserving this Lie algebra structure. So, it must be Lie algebra homomorphism. Okay. So, that is why you demand this phi to be Lie algebra homomorphism, so that the algebraic structure is preserved on the both sides. So, each x acts on V. So, in particularly we can talk about x acting on V. Okay. So, simply this means, okay, so we use this shorthand notation either x of V or x V. So, which actually just denotes what phi of x does on V. Okay. So, most of the time we will not actually tell very explicitly what is this phi. So, this phi will be always hidden. Okay. So, then we write x v to denote the action of this x on V. Okay. So, it should be understood that, so whenever we write x is acting on V, so that means we are talking about there is a representation. So, that is actually kind of plays the role. If you are not comfortable with this notation in the beginning, better you use phi x of V every time. Okay, that is actually better. So, now there are immediately some important objects that one can see or associate with the representation. So, suppose phi is a representation from the Lie algebra G to GLV. So, then there is this kernel. So, this kernel of phi, so which is an ideal inside G. Okay. So, if you take any element of this kernel, so this kernel elements will act trivially on GL of phi. So, as long as the action of G is concerned, so this kernel does not play much role. Okay. So, in particularly modulo the kernel, we have this induced map phi tilde. So, that is map from the G modulo kernel of phi to GL of phi. Okay. So, now we have changed actually the Lie algebra, but it is easy to see that the action of G can be recovered from the action of this G modulo kernel phi. Okay. There is this natural map from, okay, let me draw this diagram. So, you have a map from G to GL of V, and then you have a map, natural quotient map, which we call pi. So, that is from G modulo the kernel phi, and using this universal property of this G modulo the kernel, you can actually define a map phi tilde here such that this diagram commutes. Okay. So, I would say the action of G, like as long as you are only worried about the action of G, so that actually can be recovered from the action of this G modulo kernel phi. So, that is all I meant to say. So, you say this representation is actually a faithful representation if the kernel phi is 0. Okay. So, phi is said to be faithful, okay, if kernel phi is 0. So, that means phi is equivalently phi is injective. So, that means G can be realized as subalgebra of GL of phi. Okay. In this case, G can be realized inside GL of phi. So, this notation just says, so you have an injective map. We have an injective map. Okay. So, this is the shorthand notation. So, faithful representations are again very important representations. So, for example, as I actually stated before, Ado's theorem actually guarantees that there is always a faithful representation from G to some GL of V. Okay. That means any finite dimensional Lie algebra can be realized as general linear Lie subalgebra. Okay. So, if time is there, I will try to prove Ado's theorem, or otherwise I will give some notes. So, from there you can actually read that theorem. Okay. So, let us see some examples of Ado's theorem. Okay. Sorry, the representations. So, we already seen that there is this adjoint representation. So, that is the very first example. Okay. So, this adjoint representation, which we saw it plays crucial role throughout. So, what is this? This is a map from G to GLG. Okay. So, this is given by x goes to add x. So, the kernel of this adjoint representation is nothing but the center of G. Okay. So, if you take for example, G to be linear Lie subalgebra, so then this inclusion G inside GL of V. So, this inclusion we denote it by iota. So, this is actually a natural representation. Okay. So, this using this inclusion you can see that G naturally act on V. Okay. So, this is also a representation. So, this is you call it natural representation. For example, you can see that SL to C. So, this is sitting inside GL to C. So, naturally acts on C2. Okay. So, this representation space, so this V is called representation space on which this Lie algebra G is acting. Okay. So, that is the meaning of this. So, we will actually later see many interesting representations, okay. But in this lecture I will just introduce only the terminologies. So, now actually this same thing giving a map from G to GLV can be actually characterized as follows. Okay. So, some of the books actually defines the representation as follows. Okay. So, what is the meaning of that? So, you have for example, a vector space V, you can think a representation as follows. Okay. Here is the equivalent version of defining. So, let us see actually, like if you start with the representation, what happens, some in some sense that is what motivates us to define this. So, you have phi from G to GL of V. So, then each x in G you have this phi x. So, which is a map from V to V. So, given V you have this x V which is actually defined to be phi x V. Okay. But this association you can think, given an element of G and given element of capital V, you are associating an element of capital V. So, the same information can be actually encoded as follows. So, you can define this new map from G cross V to V, and if you want you can call it phi tilde. Okay. So, what is this phi tilde? So, this phi tilde actually map x comma V to just this x V, okay, which is phi x V. So, then you can write down actually some important properties that are satisfied by this phi tilde. Okay. So, I will leave it to you to actually write down. So, maybe if you actually want to use some other notation, maybe you can also use this as some x dot v. So, using this x dot v, you can see that this phi tilde must satisfies the following properties. So, here is the first property, these are all called module properties. Okay. So, you can take lambda x plus mu y, and then if you act it on v, then it should be like linearly act. So, you should get lambda x dot v plus mu y dot v. And then what will be the second property? The second property is x dot lambda v plus mu w should be equal to lambda x dot v plus mu x w. So, that means x is acting linearly. So, here if you take the linear combination acted on v, then again it will be linear. Then what is M3? So, this is the Lie algebra property. So, the Lie product if you take x y, if you act it on v, then this should be equal to, you first take this like commutator, okay, x. So, y acting on v and then x acting on y dot v minus y dot x dot v. If you take that, that should be equal to your bracket x y acting on v, and this should be true for all x y in G and then v w in capital V and all lambda mu in complex numbers. Okay. So, all these properties are satisfied. So, all these properties if you spell it out, these are all satisfied if you start with the representation. So, if you take this phi is a representation, and then if you define a map x v goes to this phi x v, you can see that all these properties are satisfied. And conversely, if you have a map like that, suppose if you have a sigma from G cross V to V, where x v goes to Okay, again you can denote it by x dot v or sigma of x v, whatever way you want to denote. So, then you can actually define phi or sigma tilde, whatever, okay, maybe call it sigma bar. So, from G to GLV given by this x goes to this, you can call it sigma x from V to V, where V goes to this x dot V. So, this way you can define sigma bar, and I urge you to check, okay, this is again purely checking that the sigma bar is a Lie homomorphism. Okay. So, in both way you can actually go from the representation to this, what is this called module, okay, and then if you start with this module, okay, G module, so then you can go to the representation. So, G module means it you V is said to be a G module, okay. So, V is said to be a G module if there exists field tilde like this satisfying this condition. Okay. And basically what we saw, so there is a dictionary between representations and G modules. Okay. If you take G representations, so that is phi from G to GL of V, maybe you can also denote it by V comma phi. Okay. From this you have one to one correspondence between this and what is called G modules. Okay. So, this is actually a map from G cross V to V satisfying, this is Lie algebra homomorphism satisfying the conditions M1 to 3. So, this correspondence is very clear. Okay. So, that is what we just saw. So, if you are seeing this for first time, okay, if you have not done any module theory in your algebra course, I urge you to check this correspondence very explicitly. Basically all you need to do is just check the map from phi to phi tilde. So, that actually satisfy these conditions, and from sigma to sigma bar, that is also satisfying the conditions that is given here. Because of this dictionary between G representations and G modules, we actually kind of use modules and representations more or less in a synonym way, okay, synonymously. So, we always like we sometimes say a sub representation, sub module, okay, all these are like synonyms. Okay. So, they can be interchanged, not a problem. Okay. So, now we are ready to define what is called sub representations, and then we will also show you like how to construct some new representations from old representation and so on. Again the module language will be better in the for this. Okay. So, maybe we can also okay, let us use module language. Okay. Let us not worry about it. So, you start with the Lie algebra and let us say V is also G module. Okay. So, that means there is a action of G on capital V, that is all important. Okay. That action actually obeys the Lie algebra structure on G. So, now what is a submodule? Okay. So, here is the definition. A submodule W of V is a subspace first of all, such that whenever you take x and then whenever you take V, okay, x from G and then V from W, then if you compute the action of x on V, so that should be inside W. This should be true for all x in G and V in W. So, in particularly we have this module map from G cross V to V, okay, let us call it sigma. We can restrict this sigma to G cross W, okay, which is a map from G cross W to W. So, this is actually going to give you again module structure on W. So, W becomes G module with respect to this C restricted to G cross W. So, same action you restricted to W, that is going to give you module structure on the W. So, that is what submodule means. So, that is naturally defined. Okay. So, here is the another definition, what is called irreducible module. Okay. So, once we have defined what is called submodules, then it is easy to define what is irreducible module. Okay. So, a G module V is said to be irreducible if V contains no proper non-zero submodule. Okay. So, that means if W is a G submodule, then that should imply either W is 0 or entire V. Okay. So, it is actually does not contain any other proper non-zero submodules other than like 0 and V. So, these are all the only submodules. So, 0 is being a subspace, one can easily check it is a submodule. V to begin with is a module, so it is also a submodule. Okay. So, both are called trivial submodules. So, in some sense V does not contain any non-trivial submodule. So, like in all algebraic categories, you can also define this direct sum of these G modules. So, if you start with V1, V2, both are G modules, then we can construct V1 direct sum V2. So, that is the tuples V1, V2 such that V1 is coming from V1 and V2 is coming from V2. So, then we define the action of G on this V1 direct sum V2 using the action on V1 and V2. So, you take X and then acting on V1 V2. So, it just to make it act on the coordinates x dot V1 comma x dot V2. Okay. So, this is true for all x in G and V1 in V1 and V2 in V2. So, this actually gives you action and that makes this V1 direct sum V2 as a G module. So, that is something I will leave it to you to check. So, check this star actually gives you G module structure on V1 direct sum V2. Okay. So, whenever we write V1 direct sum V2, so in this category of representations or whenever we refer G modules, okay, we always assume this V1 direct sum V2 as G module with respect to this particular structure. Okay. Sometimes you can take this Cartesian product, there will be some other actually structure of G module on this, but whenever we write V1 direct sum V2, we always refer to this. Okay. So, now let us look at some important results about these 5 dimensional modules. Okay. So, you may ask actually the following question, what we really do in representation theory. Okay. Indeed, what we are trying to do So, you have a family of operators acting on some space. Okay. So, all these algebraic objects, okay, either group, ring, algebra or Lie algebra, all of them arise naturally by acting on some space. Okay. So, we are interested in understanding how these elements of this algebraic object acts on that space. Okay. So, why we are interested in something like that? Sometimes by understanding the action of this algebraic object on this vector space, given vector space, we will be able to actually get lots of informative information about the structure of that algebraic object. So, not only that, sometimes it also help us to prove something interesting about like that space, and using the action some combinatorial results also we can prove. We will see later, but purely from the algebra point of view, we are interested in understanding for example, the structure of the given algebraic object. So, that structure actually can be like the many information about the structure can be obtained from its action on some non-trivial space. Okay. So, how one actually really understand the structure? Okay. So, maybe let's actually so for that we need to see some examples, but anyway like we will see some examples later when I do SL2 theory and other things. Okay. Even the theory of this semi-simple Lie algebra is one application of how to use representations in order to understand the structure of algebras. Okay. But anyway, let us now see like some general facts about representations. So, we can define what is called indecomposable representations. So, what they are? So, you say okay, a representation V. Okay. So, let me use module language, let us not mix it. So, we call indecomposable let us say G module. So, a G module V is said to be indecomposable if V cannot be written as direct sum of two non-trivial, okay, that is non-zero G modules. Okay. So, trivial G module means it is just a 0 space. Okay. If you start with 0 space, there is a trivial action of G on that we call it trivial space. If V cannot be written as direct sum of two non-trivial G modules, then we call it V is indecomposable. So, what this means, in case you write V as V1 direct sum V2 as G modules. Okay. So, that means it is isomorphic to V1 direct sum V2. So, then we should get either V1 is 0 or V2 is 0. Okay. So, or V1 is isomorphic to 0 or V2 is isomorphic to 0. So, why this notion of indecomposable is actually important? So, if you are interested in understanding G modules, okay, so especially in the finite dimensional category, you can see that any finite dimensional G module can be written as direct sum of indecomposable G modules. Okay. This is just follows from induction on the dimension. Okay. Let's prove this. So, this is very important observation. Let us say V is finite dimensional G module. Okay. Then claim is V can be written as direct sum of indecomposable G modules. So, how one does that? So, if V is one dimensional, then there is nothing to prove. To begin with, V is indecomposable, then we do not need to worry. Okay. If V is indecomposable, so then we are done. Okay. Otherwise, what will happen? Otherwise, V has to be written as V 1 direct sum V 2, because V being decomposable with V 1 being non-zero and V 2 being non-zero. So, that means dimension of V 1 and dimension of V 2 both are actually smaller than dimension of V. So, this tells us that now using induction we can write V 1 as direct sum of indecomposable modules, V 2 as direct sum of indecomposable modules. So, that says V can be written as direct sum of indecomposable modules. So, this is actually a very important observation. Okay. For example, you can say that if you are interested in understanding any G module, then this observation immediately tells you that it is enough to understand first of all what are all the indecomposable modules, because any other module can be achieved or can be obtained from this direct sum of indecomposable modules. Okay. So, if you think about it, okay, this is actually very important thing in representation theory to determine what are all the indecomposable modules. So, let me give one example and then stop. Suppose if you have this one dimensional space, okay. So, this is let us say acting on this vector space V. Okay. So, I can think this as abelian Lie algebra, there is no issue. So, this x is acting on V. So, now what we are interested in? We are interested in actually how this x acts on V, and then from the for example like computational point of view, one is interested in understanding like how to compute for example the trace of x, determinant of x and so on. So, for which we need to actually get a basis B of V such that the matrix of x with respect to B should look really nice. Okay. So, this should really look nice. So, in order to achieve this, okay, so for example Jordan canonical form. So, that is actually giving you some basis. So, with respect to that basis, the matrix of this x looks like upper triangular matrix. So, not only just it is an upper triangular matrix, it is an upper triangular matrix that has, if you see from computational point of view, large number of zeros in it. Okay. So, you are interested in finding out such a basis. So, for which how are you going to find out such a basis? So, you want to write V as first of all sum of or direct sum of x invariant subspaces. Okay. So, if you write V as direct sum of x invariant subspaces, that helps you to actually produce a basis, and then that basis actually obtained from putting together the basis of each individual x invariant subspace. So, that the matrix of that x with respect to that basis will look really nice. For example, it will look like a block diagonal. Block diagonal already has lots of zeros in it. Okay. But the thing is, you want to actually kind of refine this further and further, and then you want to get like a maximal direct sum of x invariant subspaces. Okay. You do not want to get just to get the sum of x invariant subspaces. You want to get like a maximal possible. So, the maximum possible obtained from this writing this V as direct sum of indecomposable x invariant subspaces. Okay. Basically, cyclic decomposition theorem says that V can be written as direct sum of cyclic subspaces. So, that implies that if you think about it, so these indecomposable X invariant subspaces are nothing but cyclic subspaces. Okay. So, you can say that the entire this Jordan canonical form, finding Jordan canonical form or rational canonical form, everything fits into like understanding this like representation of this one dimensional Lie algebra Cx. Okay. So, to understand the representation theory, first one should understand the representation theory of this one dimensional algebra, okay, and then you can actually go to two dimensional and then see what happens and so on. Okay. So, basically the representation theory of this one dimensional over complex numbers is basically equivalent to finding Jordan canonical form. Okay. So, you can see how powerful is the representation theory. Okay. With that comment I will stop now. Okay. We will continue later in the next class with the further like terminologies in representation theory like homomorphisms, quotients and some isomorphism theorems. Okay. I will stop now. Thank you.